as you said, it's an introduction or it's induction to our course that it might be inducted in next January. So quickly, the objectives of this 2 days workshop is to, as I said, to introduce our main course, Bitfall of Seismic Imaging. The main course will be covering several practical exercises and a lot of practical technical information. The objective of the course is to handle the bitfalls resulted due to different reasons, from acquisition, processing, interpretation, amplitude-related bitfalls, velocity errors, geological impediments. So the course under the title Bitfall of Seismic Imaging is objective to resolve these issues. The strategy of the course is to know how to avoid, detect, and fix the previously mentioned bitfall, and this will be done through having enough seismic acquisition and processing knowledge required to understand the nature of the bitfalls, understand the impact of the subsurface geology, and how the interpreter or the seismic engineer can judge the quality of the seismic through doing the proper QC through the QC plans, and precisely detect the error in seismic image resulted from different seismic processing. Well, now I will go to the workshop scope. I was trying to tell you about our course, which is the Bitfall of Seismic Imaging. So today or now, the workshop is going to somehow introduce and handle these points. So the scope for our workshop today and tomorrow: why seismic method is preferable method in oil and gas explorations and other geophysical methods. Understand how is the seismic image is built. In order for the seismic engineer to have a judgment on the quality of the seismic image, first you need to understand how this image was built. Types of seismic acquisition and survey design, and what is OPN. OPN is the abbreviation of ocean bottom nodes, and it is the most recent technique in the acquisition now. So we'll have a quick look on it. The role of seismic processing, generic processing workflow and main processing steps, types and application of interpretation, and we will end up with AVO and AVA, and a little note about inversion as well. Okay, so let's start with the first point: why seismic method. This figure quickly shows the geophysical method. Okay, the presentation or the slides will cover all the levels, either students, geologists, geophysicists, and there will be basics information and advanced information as well. So quickly, why seismic method? Geophysical method, as most of us may know, it's have a lot of sectors: gravity, magnetic, electromagnetic, electrical, seismic. Seismic method mainly, the geophysical methods mainly divided into two main parts: the active methods and passive methods. Active methods like gravity, magnetic, radioactive, and passive methods like seismic method. The main difference between the passive methods and the active methods, that the passive methods detect variation within the natural field associated with the Earth. That means that the properties that we are measuring is naturally coming out of the Earth, like the gravitational force, magnetic, and some electric and radioactivity and geothermal methods. So you do not have to induce anything to the Earth. It's naturally measured. Active methods are artificially generated signal transmitted into the ground and then modify the received signal, like the seismic. A quick comparison between the gravity methods, magnetic and seismic. The gravity data can be used to define regional tectonics, and gravity anomaly are caused by heterogeneity distribution of rock of different density and depths. So the gravity method depends on the density or the variation in the density between rocks. The limitation for this method, why it's not used in oil and gas exploration, because it has low resolution than seismic. In terms of mapping and interpretation, it has lower resolution. The magnetic method, magnetic data may be used to separate basin from non-basin, define the shape and form of a basin. So the magnetic method mainly is to delineate the basements. And as well, it has lower resolutions than seismic, so it is not used in oil and gas exploration. It is used for regional exploration or regional studies. As I said, magnetic is used to delineate the basements. Well, for the seismic method, the application of the seismic method used in interpretation, horizon mapping, to get velocity information and the fluid velocity. The HI, which is the direct hydrocarbon indicator, we will talk about it later. Seismic data can be integrated with well log data. Seismic help in well location decision, help in understanding a lot of reservoir properties. Does seismic method has limitation? Yes, it has. Some limitation in the resolution for the very thin layer. Sometimes the wavelength of the seismic doesn't capture the thin layers. A high change in topography makes the acquisition a little bit difficult. Resource limitation due to large amount of data, which directly increase the time and cost of the process. As we go forward in the technology, much more cost is needed and more data size is added. So the seismic method application is divided into three main parts, as most of us know. Seismic acquisition, which is a step of acquiring the data. Seismic processing, which is filtering the data and removing the multiples, adjusting the velocity, doing the migration. Seismic interpretation is the third and final step, where interpretation includes more analysis rather than horizon and fault picking. Also, interpretation include defining the petroleum system, doing the analysis of the reservoirs, all of this. Okay, I will cover now a few concepts and fundamentals which will help us to understand what's going on. One thing to mention again, we are trying to understand the pitfalls related to seismic, either it's coming from acquisition, processing, or interpretation. So to understand the pitfall happens in the seismic image, we need to understand how the seismic image is built. To understand how the seismic image is built, we need to define some concepts. First one is a wave. Seismic wave are wave of energy that travel through Earth. Waves can travel through a body, wave, or along the surface of a body. Wave front. Seismic energy can be considered as a wave front or a series of rays emanating from the shot. The wave is represented by the ray path. So in our reflection series, we do not use the wave, we use the ray path. What is the ray path? Simply, the ray path is a perpendicular line every way to a wave front. So this is a wave front. This is, you can consider this as a source, this point as a source. So the wave is propagating down, and it's represented by the ray path. the parameters wave. I think most of us studied this in the physics in the school or high school. So the wave consists of several parameters like the peak and trough, amplitude and period, and wavelengths. As most of us know, the peak is the maximum point for the amplitude, and the trough is the minimum point of the amplitude value. The reflection itself. So this is a very important slide. If we had a look on this figure, we have the shot and the receiver or detector or G-phone. So this is the first reflection, received, second reflection, and received, third reflection, and received. The point where the reflection occur is called common midpoint. Okay. Now we will try to imagine the trace coming from the reflection. It will be like this. Do we only have one trace? We have a lot of traces. Each trace represents the CMB. So from the first shot to the first detector, we have one trace. And from the second shot to the second G-phone, we have another trace. When we gather all these traces together, we create something called CMB. And when we gather different CMBs, we create the stack. Okay, we can see here the trace takes two behavior. Okay, one to the left and one to the right, which is peak and trough. The positive fill is peak, the negative fill is trough. Now let's say why this happened. It's something related to acoustic impedance and reflection coefficient. So reflection coefficient is the ratio of the amplitude of a wave reflected off an interface to that of the wave incident upon it. According to the equation, acoustic impedance equal ρ2 V2 minus ρ1 V1 divided by ρ2 V2 plus ρ1 V1, where the ρ here is the density and V is the velocity of the layer. The reflection coefficient is acoustic impedance of the second layer minus acoustic impedance of the first layer divided by their sum. The reflection coefficient will be trough if it is negative and will be peak if it's positive. For more clarification, if we have here three layers, the first and third layers have the same ρ1 V1, the same acoustic impedance. So we need now to calculate the reflection coefficient according to the equation. Okay, so if ρ2 V2 is less than ρ1 V1, we will have a negative RC. Again, if we use the equation of acoustic impedance to calculate the reflection coefficient, if we have ρ2 V2, which is the acoustic impedance of second layer, less than ρ1 V1, we will have a negative reflection coefficient, which will give us trough. This one, the red one. If ρ2 V2 is greater than ρ1 V1, so we will have a peak. So that's how we create the CMB gather, and that's how we create the stack, and that's how we get a peak or trough. Why I'm saying or explaining this? Because in the interpretation and the AVO analysis and AVA, the polarity is doing an important job in detecting the different type of gas. Now we'll turn to the seismic acquisition. Mainly, in seismic acquisition, we have 2D survey and 3D survey. 2D survey might be regular enough to provide high resolution like that of the 3D. But the main advantage of the 2D than 3D, normally 3D survey or acquisition is better because it's getting more coverage. But one of the advantage of the 2D that the irregularity of 2D survey is useful in large extended version area, where we need to have all possible information with minimum cost. The 2D survey or 2D lines is cheaper than the 3D seismic. So if, for example, you have a new area or a large area, it is better to acquire 2D data at the beginning because it's cheaper. And it will give you more coverage. 2D area, 2D surveys also very useful in complicated topographic concessions. So for this, for example, this part or this area, we have the red lines. This is 2D lines, okay? 2D acquisition or 2D lines was used for this area because it's almost impossible or very difficult to have a 3D regular survey. The nature and the topography of the area make it very hard to have a 3D survey. So the only way to acquire seismic data here is using 2D lines. So that's one of the advantages of the 2D lines. Some areas, it's impossible or difficult to acquire, and it will be very costly to acquire 3D seismic. That's a quick comparison between 2D and 3D layouts. As you can see, the 3D survey is consisted of intersecting inline and crossline. The white triangle here is a point of coverage or the CMP. So the red triangle is the shot and the yellow circles is the receiver. So we are expecting to record this point more than one time, about 1, 2, 3, 4, 5 or more, about 6 times. And the same point at the same location for the 2D, it will be covered only 1 or 2 times. So the coverage or the time or the power or the fold of recording the same point for the 3D survey is much better than the 2D survey. And that's result in better resolution. So this is the same stack. This is a 2D survey or 2D shooting. And this stack resulted from the 3D shooting. Next point is the type of acquisition. We have several types of acquisition: marine, land, OBC, 4D, boreholes. So in the marine or the offshore, vessels use 1 or 2 air guns as sources. A streamer towed to the vessel where streamer contains the receiver hydrophone. In the marine acquisition, the data is recorded by hydrophones. And the source is the air gun, which releases high pressure, which reflects back on the layer below the sea surface. The reflected energy is recorded instead of hydrophone, as I said. For the land acquisition, it's somehow more difficult than marine due to numerous types of terrain and near surface problem, and the changes in topography. Sometimes we have dunes. Land energy source are explosive and vibro size, and the detector here is freeform. We have a transition zone. Transition area is shallow water between land and marine, where here, in this case, we use both G-phone and hydrophone for recording the data. The OBC, the ocean bottom cable, it's containing, what is the advantage of the OBC? It's very close to the transition one, but the advantage here is that we are using a 4-component receiver. The 4 components are 3 orthogonal G-phone and 1 hydrophone. So it's a mix between the offshore and onshore. Well, now I would like to mention the OPN. The OPN, the ocean bottom nodes. We will talk about OPN layout and why we are using OPN. The OPN is a new acquisition technology and new technique. It's quite similar to the OBC. It is using 4 components as well. 3G phone and 1 hydrophone. Okay, the one on the left is the OBC and the one on the right is OBN. What is the advantage of the OBNs and OBC? As you can see in the figure, the OBN, ocean bottom nodes, are not using cables. The OBC are using cables. The OPN is not using cable. How this is done? With new technologies, what's happening that the ship puts the nodes. The nodes is about something like stations. It is put on the ground without using cables, using only robots and machines. This makes the acquisition process more flexible. So we are not using cables. Also gives the advantage to acquire the data in difficult places, such as the data acquired around the rig or platforms. Also, the OPN has an advantage from the streamer. Also, the streamer is using cables. So you can acquire data around or below the rig floor or the platforms around them, because you are not using cables. So OBN is multi-component seismometer located on the seafloor, which could independently collect and record seismic signals. OPN do not need cables to transmit the data, which make it flexible tool, result in higher quality data. OPN can acquire data below the platform. Streamer cannot do this. And this is an example for the difference between the quality. The one on the left is acquired by streamer data, and the one on the right is acquired with OPN. You can see here that the seismic image is better on this side. Also within this layer, the seismic is better quality. The survey design. One of the important points in the survey design, in the exploration process, before deciding where to do the acquisition and processing, the ultimate goal of conventional processing is to obtain a 3D volume of seismic image. The image quality from migration depend on the stack quality and accuracy of the velocity field. However, there is 2 main factors affecting migration: aperture and spatial sampling. Migration, for who don't know what is migration, it is the main process done in the seismic processing to achieve correct subsurface image. So the survey design, it is something that designed before the acquisition. Okay. For example, migration moves event C-D- on the time section to its true subsurface position CD. So C-D- after we perform the migration, the reflection turned to be the CD. Okay, what's happened from C-D- to CD? The event is steepened and more sharper, and the depth increase. That's what the migration do. C-D- we correct the velocity field and correct it to CD. Okay, so migration shortens the reflector length of CD in geological section. Migration moves the reflection in the upward direction, so from C-D- to CD. In the if the recording were confined to if line lengths were confined to OA during recording, then the time section would be blank. If the recording were confined to A, B, then event C-D- would be absent from the migration section. Okay, let me explain what this. Here we have the shot and receiver. Okay, the shot and receivers. If we only shot from A to B, or we are recording from A to B, we are not going to see the CD after migration because it's limited only here. And if the recording were also confined to AOA, the CD will not appear at all. So the conclusion that the recording line length should be long enough to include significant part of the fraction that may be present. Also, recording time must be long enough. So we have to have a record length, a full record length covering the event that is going to be migrated. Also, especially for the offset, we have to have enough coverage so when the C dash D dash is migrated, it will be covered. Why we are saying all this? Because from previous observation and conclusion, we can now recognize between subsurface area, target or image zone, and recording area. The main task of survey design is to have a subsurface area, recording area covering the subsurface area. If we have a certain structure or target, okay, we have the migration or the recording area, the migration aperture should be covering the target or the structure. This is our target. For example, it extends for 4 kilometer by 4 by 4 kilometer. So our aperture or survey design or the recording area should be exceeding it. So when we are going to migrate this one, it is moved up depth. So if the recording area is not covering the reflections, you will not be able to see the reflection after migration. Okay, I know it somehow it's advanced, but in our course it will be explained in more detail. We will go now to the seismic processing, the second step in our workflow. Most of us hear about seismic processing. The role of seismic processing simply is to make the image clearer or to make the signal and ratio increase. The seismic processing is done through processing to detect the velocity for different fluids. Also, seismic processing helps to get a better or free noise amplitude map that help the interpreter. This is a generic processing flow. The processing flow starts with reformatting the data. The reformatting process is to read the data from SIG-Y or SIG-D format to the internal service company format. After this, you do trace editing, geometry update, amplitude recovery, noise attenuation, deconvolution, multiple attenuation, velocity analysis, regularization, then migration velocity, migration post-stack sequence. For our workshop, we will go through a few of these steps, not all. In the full course, we will go in details for each step and the testing plan and the QC plan done for each step. But for now, we'll take care of a few steps of it. So let's start with the reformat for the SIG-Y. A reformat, the data is received from the field in SIG-D or SIG-Y format or from the client. SIG-Y is the common format used worldwide. Processing center changes data from SIG-D or SIG-Y to its internal format. Data is received as a tapes, most of the 3590 or 3592 from the field. Recent data acquisition is navigated merge. I will not go into these details about the navigation merge now. SIG-Y tapes are read in the driver of the processing center. SIG-Y QC, which is a very important point, is done by building different maps to be compared with the navigation data map or map from the field. Usually we receive the data from the field and we receive a QC from the field. After reading the data, we build the same maps and compare it with the maps we got from the field. Reformatting also is done after finalizing the processing. After we finish our processing, the data is retransformed again from internal format of the surface company to the SegWi. Next step is the trace edit. It is removing bad shot from record if exists. Bad shot is due to dislocation in source or any error occurred during the shooting process. Sometimes while acquisition is done, some of the detector is moved or relocated, so it causes some noise and some error. The bad shots that we need to remove is mentioned in the observer log. The observer logs, simply it is the log showing every single thing happened for the source and receiver in the field. So in the observer log, it is mentioned if there is some error happened in the field while shooting. That's a zoomed bad trace that need to be removed. This is simply a shot in the seismic record, and we have a bad trace. It is removed, and this is the QC done. We subtract both records from each other, and we make sure that we didn't remove any primaries or amplitude. This is the primary, and this is the primary reflection. How this is done, I will explain it now. We will go to the noise attenuation and frequency filter, and I will explain to you how this is done in the processing center. So the noise attenuation step, I can go a few slides back to the flow. So we talked about the reformat, trace edit. Now we are going to talk about noise attenuation. As you know, the seismic record is consisted of seismic traces, as we said earlier. So not all the seismic traces is good, or not all seismic traces have a good reflections. So the noise attenuation is simply discriminating between signals and noise. Signals that carries desired information, noise are signals, but they are unwanted signals. The noise are divided into two main parts or two main types: random noise and coherent noise. The random noise, from its name, energy which does not has a correlation from trace to trace, so it has no trend. It's not trendable, like something called swell noise, instrument noise. For the coherent noise, it's predictable from trace to trace across a group of traces. So it has a trend. It is repeated. That's an example for different kind of noise on the shot record. We have something called reverberation energy, surface wave, air blast, facility noise, vehicle noise. Okay, most of this noise, and this is ground roll noise, most of this noise are produced during the acquisition process. Some of them could be avoided while acquisition, and this will be also taken care of in our main course. Some of this noise can be taken care while acquisition, and some of them is handled in the processing center. We have different kinds of methods or techniques to resolve the noise attenuation. One of them is frequency filter. As we talked earlier, also, we have the wave or the trace has different parameters like frequency, amplitude, velocity, phase. So each type or each kind of noise attenuation depend on one of these parameters or several parameters to remove the noise. Again, the noise is unwanted signal. So the noise are trace. It has an amplitude and it has phase, it has velocity, all of these parameters. So the noise attenuation process is how to use these different parameters to remove the unwanted signal. One of the methods is frequency filter. So we are here dealing with the frequency factor. For example, we have here a bad trace. As you can see, it has higher amplitude than the surrounding traces. Okay, and here the record after removing this noise, and this is the difference between the two records or two amplitude, to make sure that we removed only the high amplitude. Also, for example, this one, this is removed here. Also, this one is removed here. Okay, let me tell you what's happened practically. What's happening for a certain number of traces, we create a window, okay, like this, and tell the algorithm, or tell the what we can say, tell the processing is done through math and physics inside a job or a workflow. Okay, so here we detect or decide a window, okay, within certain number of traces, for example 21 traces or something like this, and we calculate a median for the amplitude. So the trace has an amplitude value. We calculate a median for this window, and we call it K. So the K equal, for example, equal 6, which is the median value, the median amplitude value for this group of traces inside the window. Then the system or the workflow do a comparison inside the window. So this window consists of a 21 trace. So we get the median, which is equal 6, and compare it with the first trace. Okay, if the amplitude of the first trace less than 6, it will be kept, it's not deleted. And the second trace, third trace, fourth trace, the median compares the amplitude of each trace within the window until he finds amplitude higher than the median, so it removes it. That's simply what's happened here. One of the kind of the frequency filter. So you calculate the median for group of traces and compare this median with the amplitude of each trace within the window. If the amplitude of the trace exceeds the median, it will be removed. And that's what simply happened here in the frequency filter. What I want to say here, that each step in the processing depend on certain element or certain parameter. For example, here we depended on the amplitude. Okay, why it's called a frequency filter? Because within this window, I am deciding and I choose a certain range of frequency. For example, for this window, I chose frequency range from 5 to 20 hertz. So when the algorithm or the workflow is going to remove trace, it will remove a trace with amplitude higher than the median and within a certain frequency range. That's how most of the processing steps works. It depends on one of the main parameter of the wave, either frequency, amplitude, velocity, one or two, or maybe three factors or three elements or parameters can be used together. Here we use the frequency and the amplitude. Okay, again, back to the workflow. One of the most important points in the processing is the velocity analysis. What is the velocity analysis, or what's done? I would like to, yes. This is the stack that we have after gathering the CMPs. Okay. What is the normal move out? What is the definition of the normal move out? As you can see here, we have the shot, okay, and the receiver here, and the distance between them is called the offset. Here we have different recorded trace. This is one trace, and this is second, third, fourth, and as the offset increase, or as you get more away from the source, you gain or you acquire the record acquire more time because the distance increased. Okay, if we shot here to here, okay, it will take less time than recording a further point. So the main reason for the move out is the offset increase, the variation of reflection arrival time due to variation in source receiver distance, which is the offset, which results in hyperbolic behavior on the CMB gather. However, the reflector is horizontal, but the reflection takes the hyperbolic shape due to this increase in the offset, which take more time. So simply the normal move out or velocity analysis is compensating this time, the delta t. When you compensate this time, the reflector goes back to its horizontal original position and it will be flat. How this is done? That's quickly the definition. That's the CMB or the traces before the NMO, which is taking the hyperbolic. After compensating the delta t, it will be flat like this. If we put the faster velocity, it will be overcorrected. Faster velocity mean the less time, and if we got a slower velocity, it will be undercorrected, which which means slower or it take more time. How this is done on the seismic processing? This is a velocity analysis. We create samplings, okay, and this is the CMB before the NMO, and this is the CMB after NMO. What does this semblance represent? The semblance represent velocity distribution, different velocity values, okay, and this is the record length, and the orange green points or colors is the amplitude distribution. It's something like a coherency display. So whenever you have similar traces around this point, you will have a clear orange point here, which we do a click on it. After you click on it, if it is the correct velocity that compensates the delta t, it will be flat like this. So you try different one. You try different velocities until you get this flat reflection. After having this flat reflection for one CMB, you do it for several locations and several CMPs, and that's how you have a good horizon on the stack. But if you try to have several CMB gathers or try to stack CMB without NMO, it will not give you the good reflector. We'll flip between these two slides, stack before velocity analysis and stack after velocity analysis. I will do several flip, and then I will show you where is the place of the enhancement of the improvement. For example, this point, sorry, this is before and this is after, before, after, before, after, before, after, another point here, before, after, before, after, before, after. So the flatness of the CMB is very important. One of the main points also in the workflow is the multiple attenuation. The multiple is simply that the primary energy is reflected more than once. Multiples are event reflected more than once. The multiples technique or methods, we have several. The multiples method like the noise attenuation. For the multiples, we have a velocity-based technique like radon and FK. Predicted multiple and subtraction. The most common technique in the field is SRME, surface-related multiple attenuation. Also, there is a predictive deconvolution and wave equation-based forward model, and this is one of the advanced recent techniques. I will go directly to the example of the multiple attenuation. This is a CMP gather where we have the multiples. This one, it's a hyperbolic, slower event than the primary. Why it is taking this hyperbolic shape? Because it is take more time. The multiple, from its name, it is reflected more than one time, so it takes double the time of the main reflected. Take double the time, so it take more distance, so it will be slower or take the hyperbolic shape. This figure is after removing this multiples. Before and after, before and after, before and after. Okay, how this is done, we can explain why or how this is done. First of all, before doing the multiple attenuation, we have to correct or do velocity analysis or do the NMO. Okay, we have to do the NMO first. After doing the NMO, we will have a flat gathers and the multiple will be slower. Okay. In this method, we are depending on the velocity of the layers, on the velocity of the horizon. So we are discriminating between multiples or unwanted signals and the signals that we want or the main reflection with the velocity. We do the velocity analysis and make the gathers flat so we can discriminate between it and the multiples. Then we remove the multiples. Another technique, it's called SRME, which is very common in the industry, surface-related multiple elimination. Surface-related multiple elimination, or SRME, uses the recorded seismic data to predict and do iteration to subtract the multiple series. It's some kind of an iterative method, and it's a 3D method as well. For example, if you had a look on this input, you will never expect that these reflections are multiple. Okay, but after doing the SRME, this is the true reflections we have, and all of this was multiple. Okay, how this is done? It's a 3D modeling where it predicts the multiple through iterations. One of the QCs done on the multiple attenuation is the semblance that we just explained in the velocity analysis. The semblance, as we said, is a coherence or amplitude distribution with the velocity distribution. So the multiple characterized with low velocity and a little bit amplitude, have a little amplitude and low velocity. So after removing the multiples, we can't see anything here in the lower velocity. So that's one of the QC. That's a velocity QC. Okay, that's all for today, the first day of the workshop.